is Lauren Soos, who's the Senior Sales Manager at Senior Marketing, Senior Sales and Marketing Manager at TRS Group. Lauren has over 20 years of experience in the environmental consulting and remediation industry, including the last 10 years managing complex thermal remediation projects across the country. Currently, Ms. Soos is an environmental engineer and manages sales and marketing for the TRS Group. Welcome, Lauren, who's going to present thermal desorption of PFAS-containing soil, lessons learned at an in situ and ex situ implementation.
Thanks, everyone, for being here still. I know we're all in a rush to go get our spray tans this afternoon with our friends next door. As Michael was just describing, I have had a career focused on remediation, environmental engineering, and about 14 years ago had the pleasure of implementing my first ever thermal remediation project. And I have to say I've been addicted with those technologies ever since. So it's nothing but thermal for me. I do have those blinders on, and feel lucky to be here today talking about a couple of very recent projects that we've worked on. And when I say we, I'm referring to the team that's doing the work. These are projects that have been funded by Department of Defense's ESTCP program. So for those familiar with that, R&D grant arm from Department of Defense, ESTCP is all about taking technologies that might be in the lab or have new potential applications and demonstrating their ability in the field. So this photograph that you're looking at here on this cover is an in situ project that was funded by DoD, but I'm also here to talk about an ex situ application that we also did under that program. So just taking a quick step back, assuming no one is geeky like me when it comes to thermal remediation, although I do have a former colleague here in the audience, so there are definitely some in the audience today. But in situ and ex situ thermal is all about putting heaters or electrodes, some type of heating infrastructure in and around soil to get up to temperatures where we're volatilizing contaminants. And then at the same time, collecting the soil vapor, the steam, the contaminants as they are being released from the soil. Typically, most of the projects that are implemented in the thermal world are chlorinated solvent type of projects. So we're going after like dry cleaning waste, manufacturing related releases that have occurred. And we are usually implementing these technologies actually below the water table. Now, below the water table, or whenever there's water in the matrix, the maximum temperature of that soil is going to be the boiling point of water. So for the projects that I'm talking about today, we are going to temperatures well beyond the boiling point of water. So it's key for those types of projects that we are targeting vadose zone applications, and that's the in situ project that I'm going to be discussing today, or ex situ applications. So it's soil that at this particular site had PFAS within it, so it could not be shipped off-site per the order of the Air Force. So all of this waste was just being containerized. It was the result of basically building construction and demolition that had occurred over a few years, where stockpiles of this PFAS-containing soil material were being held at this base. So taking a look at the different types of thermal remediation technology, in order to get to the high temperatures that, again, I'm going to be talking about today, there's really only one technology that can get us there, and that's thermal conduction heating. The company that I work for, TRS Group, refers to our branded thermal conduction heating technology as a flex heater TCH technology. So you'll oftentimes hear me refer to flex heaters or TCH. So just a quick note about some of the acronyms or brand names that I might be using in this presentation. There's other technologies that are out there, but again, those are lower temperature strategies that are more suited for like chlorinated solvents, petroleum hydrocarbons, et cetera, et cetera. So TRS has a bit of a history outside of these two projects on the R&D front. For years, we've been involved in developing patents and various different optimization tools for the industry to help implement these technologies. Our flex heaters are patented. Some of our other technologies, Optiflux, electrical resistance heating, we do hold some patents for that technology as well. And we also established a patent for the thermal desorption of PFAS from soil under our R&D arm at TRS Group. So this is a video, and I am now suddenly confused as to how I'm going to be able to play it. There we go. So that was easier than I thought. But this is the installation of one of those TCH heaters. This is, full disclosure, not a PFAS site, but here you can see one of those heaters going into the subsurface. It just slides right into a conduit that is installed. I mean, at this particular site, we're inside of a building, so we're using a lot of those small mini-sonic rigs that are amazing and flexible and can put lots of infrastructure in the ground for us at high angles. You see that heater right there in this screenshot? So you essentially have a wire that's going in the ground, and the wire heats up that steel conduit casing that's in the subsurface. The actual borehole itself is grouted. It's not your typical monitoring well. It is not screened below grade, but it heats up that casing to several hundreds of degrees Celsius, and thermal conductivity of the soil essentially controls how fast that heat radiates out from that casing. And you're waiting basically in the field for soil particle to soil particle heat transfer from one particle to the next. And you have temperature monitoring infrastructure that is installed throughout these treatment volumes. So right next to the heater, you also have temperature monitoring points that are installed in between heaters so that you could see that heat front as it moves through the subsurface and crosses over with the nearby heat front from the other borehole. So that's how it works, and that's usually how we're monitoring the performance of these systems once they're installed. So about 6 years ago, TRS and that R&D arm within our company started looking at PFAS. We started receiving a lot of questions. Folks are typically using thermal remediation technologies when you're dealing with source material. And in the PFAS world, when you start looking at AFFF applications, you are typically dealing with source material. So we started, first and foremost, a literature review of what temperatures do we need to get to in order to volatilize or reach that boiling point to release these compounds, potentially from the soil. And this is just a plot with temperature on the left-hand side of the screen. Temperature, starting with 100 degrees, so right around our chlorinated solvent type of goals at the very bottom, all the way up to 500 degrees. On the left-hand side, you see a lot of different compounds that are not PFAS related. But those are just examples of thermal remediation projects that have been completed for those types of contaminants of concerns. But you can see the history of thermal includes a lot of different temperatures that have been the goals of some select projects. There's not many high temperature projects out there, but there's certainly some great examples of getting to temperatures that are necessary to release these PFAS compounds as well. What you're seeing on the right-hand side is just an example of some common ones that we hear about the most. Today, I am going to talk about PFOS and then PFOA, because those were the two compounds that our clients were looking at with the soil that we dealt with at our site. So looking at those compounds, literature tells us around 200, just a little bit below 300 degrees, we should be at temperatures where we're able to volatilize those compounds. So the next step, we went into our laboratory to do some bench scale testing to go ahead and prove that at those temperatures, we're able to release those compounds. And actually, we looked at more than just those two that I mentioned. There were about 24 compounds at the time, given the analytical capabilities then that we were looking at. So that's what's captured with the total PFAS over here on the left-hand side. And what's plotted here is just different temperatures that we targeted. So unheated, we did use a spike sample, so you're looking at part per million as a starting point. And then at 300 degrees Celsius, again, that was the boiling point, right? Right around the PFOS. So we thought for sure we were going to have a great reduction. And we had some reduction. We did not have enough. You know, in the thermal remediation world, we're used to dealing with 99.999% reductions. So this is certainly not that. So we took it up a notch. Actually, there were several different rounds of testing that were conducted. This is just a plot of some of my favorite data. But at 350 degrees Celsius, it was respectable. You see there we got 99.9%. And then at 400 degrees, it was non-detect across the board. So somewhere in between 350 to 400 degrees became our target. And, you know, looking at the boiling point temperatures again in that previous slide to what we found once we were dealing with soil, you know, there is something about the van der Waals forces of this soil and how sticky these compounds are, you know, that carbon backbone. It's difficult to release. So what you're seeing here, the reason why we think we have to go to these higher temperatures is to actually start to break down TOC in the soil, and then you get that release of these compounds that occur. So I mentioned before, ESTCP has funded a couple projects. One was completed at Eielson Air Force Base. Operations at that site concluded in December of 2021, and we were able to move that equipment out of Eielson. We took a break during the Alaska winter, but remobilized in the spring, collected our equipment, and then moved it to California for a much more beautiful weather sort of a situation. But the in-situ application occurred at Beale Air Force Base. And the latest and greatest project right now, we're getting ready to roll back into Alaska at the J-Bear base, and we're going to do another ex-situ application there. But 2 ESTCP projects, which I'll go into in a bit more detail, and then Defense Innovation Unit funded this most recent one where we're going back to Alaska for a much larger volume of soil. So Eielson Air Force Base, this is what the little soil pile looked like. This is shortly after we installed our flex heaters into this soil pile. So we did go below the ground surface with this heating infrastructure that you're seeing. You see, you know, toothpicks basically sticking out of this soil pile every which direction, and even some angled around the edges to ensure heating at the base of that soil pile. You're seeing it now before it's being covered. So when you're getting to temperatures, at this high, you need to ensure minimal amount of heat loss during operations. So the next step at this site was to cover everything, and we used a waterproof material at the base that had that had the ability to be exposed to really high temperatures, and then you're seeing some insulation put on top of that, and then finally you have another waterproof cover that covers this entire soil pile. And you're seeing this site without any of our equipment there, so that this is just the heater installation phase at this point. This is what it looked like in the late summer, early fall. So already looks like winter there. You don't get conditions like this in Florida. At my home in New Hampshire, you see something like this, but more towards those winter months. So what you're looking at here is the soil pile. And something I would like to point out here is the snow that's at the base of that soil pile. We love to see that, right? That means the insulation, this soil pile is hundreds of degrees Celsius when this photograph is taken. So you want to see, you don't want to see snow melting, right? That would mean that we've got a heat loss occurring. So we've got insulation that's working really well. Right underneath the insulating layer, you've got 300 degrees Celsius and climbing when this photo was taken, so pretty powerful. But just an example of some of the equipment that we mobilize for systems like this. You've got some of our power controls right here, a breaker panel, and then of course we've got our water and vapor treatment equipment that was put within a shelter to help support winterization when we were dealing with conditions, as you can see on the outside. And then over here in the corner is a vacuum switch. We like to monitor vacuum within the area that we're treating. So this is actually within, it's monitoring the conveyance system, making sure that we have pneumatic control over that soil pile. So we are applying a vacuum to the area that we're heating, again, to ensure that we've got that soil gas, the contaminants being pulled through our treatment system. If this thing does not read vacuum, it then shuts down the heating element. So that's the idea with that vacuum switch there. So during the heat up operations, you see things starting up here in September and then concluding, I mentioned December 2021, so it's a really short duration. You've got a great heat up response right at the very beginning. We did end up experiencing a power outage at Eielson and actually ended up bringing out a generator to the site to help normalize some of the power issues that we had. So that's why there's missing data right here, is because there was a shutdown that occurred over a couple of days. But you've got great heat up right here, and then you've got things that plateau. And you typically see that when you're dealing with soil and high temperature applications. What you need to do is boil off that water. I mentioned rather earlier how the maximum temperature of a matrix with water in it is going to be the boiling point of water. So that's what you're seeing right here. That maximum temperature that we can achieve is the boiling point of water, so right around 100 degrees Celsius, while the water was in there. So as we're collecting that steam, we're getting rid of water. There's no source of water returning back into that soil pile because it is covered. So only once the steam or all that water content is removed, do you then start to see that climb. And you've got lots of temperature monitoring here. So there's 4 different lines, multicolored, and then a gray line in the background that just represents the average there. So this is a snapshot of temperatures collected from this soil pile. There's a lot going on here, but just to walk everyone through it, all the red dots represent our heaters. There's a high density of heaters at this site. Again, we're getting to high temperatures, so you need that infrastructure spaced really tightly together. And then at each and every one of these boxes with data that is represented there in a table, you've got 3 inches below grade all the way down to several feet below grade that is looking at temperature with a specific depth interval. So right below the insulating layer, you've got temperatures between 300 to 350 degrees Celsius. And then below that, you've got higher temperatures. So the average at this site at around the time of closure was about 400 degrees Celsius. Around our heater casings, so these boxes just represent data that's being collected from temperature monitoring. Right at the center of temperature monitoring, or not temperature monitoring, heater points around it. So we're looking at the centroid, what would be the coolest point. We also have infrastructure where we're monitoring temperature right next to the heater and taking a look at how that heater is functioning. So we essentially pegged either side of our thermocouple. The maximum heater casing was at the max level of our thermocouple, and then the low for those thermocouples were recorded at 38 degrees Celsius, and that was outside. So the results from this study, again, I mentioned we're really only looking at 2 specific compounds, PFOA and then PFOS. PFOA, which does have that lower boiling point, the data was very straightforward. After the thermal remedy was implemented and the soil samples were collected, all the concentrations of PFOA were all below the detection limits. PFOS, I mentioned how some of the soil was around 300 to 350 degrees Celsius. Anything that was essentially below, or any soil that got to temperatures that were less than 350 degrees Celsius, we did see some residual PFOS. We saw a significant reduction, so you see starting concentrations here, but there is a little bit of a bar there. And the result, the hypothesis at this site was you really do have to get to temperatures around 350 degrees to get that PFOS to release. So we're working with Brown University at this study, and we had them take those soil cores and actually heat them up to temperatures at 350 degrees. And what we saw after that laboratory heat up was non-detect at the end. So that was a really key lesson learned for us as we rolled this project into the field again at that second location. And that was at Beale Air Force Base. I promised you better weather at Beale. So Beale's a little bit further outside of Sacramento, not necessarily next to the palm trees, but the sunsets, as you could see, were absolutely gorgeous. This is an in situ application, and at this particular project, we are working with Jacobs, Colorado School of Mines. Those were the folks that we were working with. So here's, again, that equipment layout. You're seeing a lot of similar equipment without all of the winterization that we were dealing with at the Eielson project. You've got a very small area that we're heating. This is now, because it's in situ, we're targeting the vadose zone. So well above the water table at this site, or what was known as the water table. That's a hint to where we're going here. The process flowgram, this project allowed the opportunity to really take a look at vapor data. So there was a lot of samples that were collected for vapor analysis using OTM 45. So we were able to collect samples coming out of the subsurface right here, just following along. You then have a scrubber that is quenching the vapors, and then we've got vapor GAC. The vapor, process vapor, is all passing through GAC prior to discharge, and then you've got another sample location, this red dot. So red dot right before GAC, and then another red dot right after GAC. And then on the water side of things, the condensate, the scrubbing liquids that we're dealing with is all passing through GAC there as well. So at Beale Air Force Base, we, again, another really quick duration of operations. Similar temperatures achieved, so average, we're looking at about 400 degrees Celsius, and you can see that temperature data that's plotted here. This red line represents the site-wide data. I've got things separated out into two different sides of this site. So California, not a normal winter last winter. They experienced record storms, high-intensity rain events, and unfortunately, we were right smack in the center of it during this project. So we did deal with some perched water that continued to feed the eastern side of this small treatment volume that we targeted. So we've got two different areas that we're monitoring here. This red line, dark red line, represents the western edge of the site, or western side of the site, and you can see temperatures were well beyond 400 degrees Celsius there as we continued heating. And then you've got this yellow side, the eastern side, where we track down the water, and you've got, again, that stagnant temperature that we talked about below, where we're stuck around the boiling point of water because we're being fed water from this perch zone. And so this is all great, lessons learned, another in situ lessons learned. So we're learning lessons as we're implementing this project and trying to figure out, okay, why can't we get beyond 100 degrees here? And we ended up doing some tests in the field, one of which is plotted here, where we're just taking a look at how much steam we're collecting and processing at some point during these high temperature applications. Once you get to the other side of this curve where you start to climb beyond the boiling point of water, you stop collecting steam. Steam is minimal at that point, but this data down here just shows how we continued to see steam, and then we even increased the vacuum to see how much steam we could collect, and saw that we were pulling water in, and that's this peak here. So lots of tests confirmed that we ended up having a perched water situation at that particular site. We are in the process of evaluating the data. So given the ESTCP funding of this project, there's a massive evaluation committee who has access to the data that has been generated from this site. Let me just go back real fast. By the data, I mean the actual soil data, so the PFOS, the PFOA concentrations that are coming out of that in situ soil. And what I can say about it's heading towards publication, is what you would expect given the last results. So on the western side of the site, where again we were able to get to temperatures, it's non-detect. On the eastern side of the site over here, where you did see that slow response given the water that we were dealing with, you see reductions, but you don't see the non-detect level that we were essentially aiming for. So just wrapping things up here, thermal, super powerful, removing PFAS from soil. We've got a couple of demonstrations now under our belt where we've learned some good lessons that keep on rolling into the next project. Right now, we're going to a much larger volume. We're going to be tackling about 2,000 cubic yards of material back in Alaska. These other two projects that you looked at were about a little less than 150 cubic yards of material each. There's a ton of economies with scale. I don't even want to talk about the cost of those two small projects projects given the volume of soil we were dealing with. It's just not even economic, but once you get to these larger volumes, it certainly starts to make a bit more sense. And we're using carbon so far on these 2 small projects, but are really excited about some of the destruction technologies that are coming out. So we're looking to this next project that we're working on, we're actually pairing up with a destruction technology and are going to be using carbon, but also sending another process waste line towards destruction for the complete removal and destruction of these compounds at the site. So pretty exciting stuff. I'll leave you with my contact information and hand it back to you.
Okay, our presenters will take questions now. Wait for a mic and say who you are and ask your question.
Yeah, my question is regarding your last presentation there. Did you have to introduce any air into the that one cell where it was completely sealed, it seemed, but you were applying a vacuum, and I guess you wanted to have some flow, but did you introduce any air into that system?
So we are not actively introducing any like oxygen or ambient air into the subsurface. However, since we are applying a vacuum, there are pathways for air to then move through the treatment volume. So it is, although both sites were covered with essentially not just an insulating layer at the top, but also a vapor layer or preventing vapor from air from being pulled in and vapor from leaving the area. Technically, around the sides, you would be able to pull ambient air around and then suck it up through the vapor recovery system. So it's happening indirectly. Mm-hmm.
Very good presentations, all of you. Thank you. My questions are for Dr. Hatzinger. When you showed us the soil cores in the post-injection conditions, how far away from the injection point were those borings, and how long did you wait until collecting those?
Yeah, so again, it's a pretty small plot. So, we were just sort of 10 feet. So the borings were probably 4 to 5 feet away from the closest injection point, and those were taken a month after the carbon was put in. And we'll do that again toward the end of the demo at 24 months. We'll take a couple different borings and take another look. During the injection process, you can take samples and try and see what your radius of influence is of the carbon. It's going to be different, and I think probably, as people know who inject things, there's always some preferential flow paths and things, and I think that's part of what, I always talk to the geologists, they always have these layers, everything's a fine sand, but when you really get out there, there's horizontal flow paths sometimes that can be fairly small, and that's probably part of where you saw that wide distribution in a couple of areas, but hopefully that's where a lot of your PFAS is flowing through also, so.
Thank you.
You're welcome.
My question was for Lauren. You talked about the water table being an issue. Are there any other site conditions that you want to avoid when you look at thermal treatment as an option for remediation?
Yeah, sorry. That's a good question. So, my job. Sorry. Yeah, and just to be clear about that Beal application, water was not expected to be an issue at that site, so that was a little bit of a surprise given some of the storm events. There did end up being that perched water table. When using these high temperature strategies for compounds like PFAS, your water is just going to be your enemy. So there's a lot of folks who talk to us about, can you just dewater a site? Can you hydraulically contain the site? And, especially during this demonstration phase, I think it's key to just target areas where it will be successful, and that's going to be the Vado zone, or really where it's very well controlled is ex situ applications. But I think there's been applications where there have been dewatering efforts, and it's just a bummer when those systems fail, because it's such a quench effect. I mean, you've got temperatures that change literally in hours, and everything goes to 100 degrees or less, and so much energy is just gone. So yeah, it's water. High temperature applications, water can definitely be your enemy.
Yeah, I had a quick question for both Dr. Hatzinger and Lauren. Post your application of your technologies, did you see any issues with UIC parameters in the water?
With what parameters?
Underground injection control parameters?
You're gonna have to explain to me what that means. I'm a
When-
microbiologist by training, so you can help me here.
Or at least in Florida and other states, you have baseline parameters for total dissolved solids.
Oh,
and
I see.
Different parameters.
Right. So, we will be injecting this at another base in Jacksonville. We're going to be doing a kind of a similar demo pretty soon, and we'll probably look at that more extensively. At the site where we were looking, I mean, the things that we're monitoring, there's also a polymer that goes in with this. I mean, that's one of the other things with any of these products. Carbon tends to be positively charged, and if you just shoot that colloidal carbon into an aquifer, it's not going to go very far. So there's a negatively charged polymer that goes in with it. So certainly in terms of TOC or whatever, you're going to have some polymer there for some period of time that then drops out. So that's going to probably go up. Otherwise you're injecting material in potable water typically. So that's the bulk of what you're putting in is basically potable water going into the aquifer. There's that polymer and carbon. So, we'll be looking more extensively when we do Jacksonville. The material's approved for injection in Florida. The colloidal carbon is, it's improved to be injected. But we'll be looking a little more extensively at anions, and this site also is anaerobic at the bottom. There's a lot of dissolved irons. We'll be looking more at geochemistry and I don't know what other exceedances might occur if that's what you're kind of worried about.
Okay.
Yeah, sorry, I'm not familiar with the lingo.
And with the thermal, do you see any issues with?
So at the sites that I was just describing, we weren't doing any type of injections, if that's your question.
Well, so it didn't apply.
Yeah, it did not apply. At some, so for another thermal technology, electrical resistance heating, there is oftentimes what we refer to as like an electrode wetting system that's also installed with electrodes. So within that borehole, so again, thinking about that heating infrastructure, we would put something to drip water into the subsurface, basically just to keep that electrode in good electrical contact with the native material. And so it's this little micro dripping effect that occurs. But oftentimes with that technology, we do have to go through that permitting process or check some boxes. We've been able to do projects in Florida without any issue. So we've figured out a way to navigate through it. But that's typically potable water that's being dripped down into the subsurface.
Okay. I have a couple questions for Dr. Doss and one for Dana. Start with Dr. Doss. So, in your slides, you discussed about the different definition between U.S. and EU, Canada. So you mentioned about U.S. water doesn't have ultra short chain compounds. Can you verify, is that because based on my understanding, the current methods are 533, 537, 1633, they don't report ultra short chain compound. And then USMR 3, USMR 5 also don't report the ultra short chain compound. So is that because it's not reported, or U.S. water doesn't have ultra short chain compound?
Okay, is that question for me?
I think so.
I didn't get your whole question, ma'am, so if you can repeat it.
Okay, so my understanding of current methods like 533, 1633, or those methods do not analyze ultra short chain compounds. So you mentioned about U.S. drinking water doesn't have ultra short chain compound. Can you verify, is that because it's not analyzed, or we don't have that in our water system?
We do have it,
Okay.
especially in landfill leachates. So the ultra short chains are present in landfill leachates.
Okay.
So we do see that after we develop the method for it, and that's what we see. And also, Paul mentioned about the breakthrough on the PFBA. So that is why when we go through the SPE cartridges, and the more volume of water you put through for the ultra short chain, it doesn't hold it. It just passes through. So you have to curtail the volume you put through the cartridges in order to trap the ultra short chain PFAS. So, but the landfill leachates contain it in the U.S.
Okay.
Not on the drinking water part, but there's not much data to that effect because there's very few labs who can analyze ultra short chain PFAS. Because we just released that method about 2 months ago.
Okay. My second question. So, in the forensics methods you mentioned about different methods you use. So let's say for a site, if I have data, do those analysis evaluation based on the method you mentioned now, and compared to, let's say, 2 years or 3 years later, assume there's no new discharge at the same site, would you think the results could be different?
Meaning?
Let's say you get a different conclusion about the source.
There's a slide I have in another presentation which shows the recoveries for it, and it's pretty solid at between 98 to 101%.
So I don't know if I say it correct. So let's say if I have data now, do the same evaluation versus I do the evaluation 2 or 3 years later, your conclusion would be the same, right?
Yeah.
Okay. Third question.
Okay.
So you mentioned about the typical AAAF, you have 3 to 10% of PFAS. I understand that when the firefighters spray them, they mix with some water, right? So in terms of like concentration level for that's a typical PFAS, what kind of concentrations they are spraying, like PPT level or PPM, PPB level?
Your question is too long, ma'am. I'll probably talk to you personally because I can hardly understand the whole question.
Okay. Yeah. And then last question for Dana. So I assuming that the process is a unique process for PFAS-treated carbon reactivation or regeneration. So I guess when you treat the carbon, you differentiate the carbon from a site was used for PFAS only, or what about those used for PFAS and also have other contaminants? So you use a different process to regenerate, or you do PFAS regenerate first and then go to another process for those other compounds?
No, that was our typical reactivation process that we use every day at our furnaces. We did not alter the process at all for the PFAS study.
Okay, so all the carbon goes through the same process?
Yes.
Okay.
Any other questions? I was texted a question for Dr. Doss.
Yeah, go ahead.
What is the method detection limit for PFOS in 1633?
You can go to 2 ppt.
2 ppt.
Yeah.
Okay, thank you. The wonders of technology.
Yeah, yeah.
Gene, you want to bring us home?
Yeah, I will definitely. Thank you, everybody. Great session. If you look around the room, you'll see why I left the PFAS session to the very end. So I wanted some folks in the room as we concluded the conference. Thank you very much. As wrap up, just a reminder, everybody's going to get the presentations. Everybody's going to get the recordings.